Um, Great. So I want to welcome all to the virtual workshop on AI meets CI, and I would like to kick off the first panel of the day on adoption of AI in major facilities, AI methods. Next slide, please. It's taking a bit of time to. Yes, great. So this panel will be discussing the current and future plans for adoption of AI within NSF research infrastructures, both major and mid-scale. We have a few representatives from different RIs where they'll be discussing different adoption of AI techniques and methods to enhance the operations, the data management, and the discovery and decision making within the facilities and also for the users of the facilities. So the goal of this panel for us would be to gain insights into the current adoption, to find out what are the challenges in adoption of AI in large-scale scientific infrastructures, and discuss and identify opportunities for cross-facility collaboration. Next slide, please. So we have assembled a very nice set of representatives from different major facilities to provide their perspectives on adoption of AI within their facilities. So we have Benedikt Riedel from IceCube, we have Leanne Guy from Rubin, we have Javier Duarte from CMS, and Krishna Kumar from TAC, and who would also be representing the NERI major facility. So the panel will start with introductory remarks, presentations about 9 minutes from each of the panelists, and then we'll go to a question and answer session following the talks. So I will hand it off to Benedikt to start the first presentation. Thank you.
Hello, everyone. I hope the slides are transitioning a little quicker now. So I'll just give a brief overview of what we're doing sort of in IceCube in terms of overall, but then also specific for AI, but also a little bit more focused on sort of the CI piece, since that's sort of my focus in IceCube. So IceCube itself is what we call a neutrino detector, or a high energy astrophysical neutrino detector. So basically what we constructed is we instrumented about a cubic kilometer of ice with what we call a digital optical module, or a DOM, which is essentially a light detector with some readout electronics attached to it, and they're down in these boreholes that are roughly 2,500 meters below the surface of the glacier in Antarctica. There's 60 of these modules on each quote unquote string. So there's 86 holes in total, and each hole holds 60 of these detectors. And we are looking for neutrinos from astrophysical sources, meaning we are looking for high energy neutrinos from some of the most cataclysmic events in the universe. So outside of sort of just the neutrino science, we also do neutrino physics, some earth science, and beyond the standard model physics, so mostly particle physics questions. We do sort of MEV to PeV scale. So if you do the transition, we're kind of roughly operating around 15 orders of magnitude in terms of energy of what our science does. So that is a very broad range compared to a lot of other experiments. We've been operating for just over 15 years now. We typically hit around 99% uptime for each year. So we've been operating basically continually for the last 15 years. And we're of course funded through MREFC grants, the OFSTA polar programs, and math, physics, and math and physical sciences at NSF. Currently ongoing is the IceCube upgrade. which is basically an infill, meaning that we are deploying more detectors into the center of IceCube. So IceCube becomes sort of what we call a veto. So it can sort of screen out some of the background events that we see. But the other big thing of the upgrade is that it's a lot denser in terms of instrumentation. So we have, rather than 60, we have over 100 instruments per string. And these instruments are two different types. Predominantly, there is something we call the MDOM, which has multiple detectors in it, and then the DEG, which just has two. But I mean, basically, we have these multi-facing 365 or 4 pi steradian detectors now being deployed at this moment. So going back to sort of like a little bit of AI, so sort of I've broken this up a little bit into the lenses of scientists and sort of CI professionals here. So from the scientist perspective, AI for everything all the time is kind of the current theme here. Particularly for the upgrade, any new method that we're developing is AI driven, or at least has an AI component in it. Sort of the classical methods are reaching a cost versus benefit threshold in terms of how much time you want to invest in them versus how much improvement you're going to get out versus AI. And there's also features there that AI provides that are a lot easier to deal with or a lot easier to accommodate than traditional methods. There's also many free tools available out for this. So for at least in the US, GitHub Copilot, Gemini, Microsoft Copilot, a lot of the large universities, at least in the US, get free access to these tools. And this is, of course, for our students, this is great, or our scientists in general, this is great. They get a lot of support in that way. And it just accelerates the basic things that we do. Giving me a code snippet for plot X that usually took you an hour, now it takes you five minutes, if that. And that kind of thing. So there's sort of this lowering the barrier of entry for code, especially more complex code, but then also for methodologies, it's everything all the time at this point. Every new method that we see that's being introduced or proposed it has an AI component to this. And we've actually already seen the impact of AI on our science. This is one of the more sort of bigger AI-driven results that we've had. So we've used what we call cascade events. These are they're not very well pointing on the sky, so we can't really discern individual objects with them, but we can discern large objects from the background with them. And basically, if we use a traditional maximum likelihood method or traditional methods, we could not do this. So in this way, we were able to sort of quote unquote discover the Milky Way neutrinos, meaning this is really the first time we've seen our own galaxy in a different quote unquote light or in different method than sort of traditional electromagnetic astronomy, or sort of the astronomy that you think of when you hear astronomy, sort of the photon-based one. So we've really observed our galaxy in sort of a novel way, and this has only been possible through the use of sort of hybrid methods with AI, as sort of very much a helper method, or an encoder in this case, to improve methods that we have had before. And similarly, this is our third point source. We've had other point sources, in quotation marks, point sources, meaning that they're well-resolved sources of high-energy neutrinos. All these are also driven by other machine learning algorithms, but this is really the one that I would like to highlight. From a hardware lens, I have to say there's sort of a big difference between training and inference. The training is essentially a traditional HPC application. At this point, you need a GPU or multiple GPUs, or you need multiple machines that then share information through a fast networking or low latency networking. The inference, of course, is more high throughput oriented, in terms of you want to get as much data through the inference as possible, as quickly as possible. And of course, the requirements in terms of resources are a lot lower compared to training, depending, of course, on your model. This is course, also is changing with LLMs, but sort of generally for science applications, I would say we're still sort of in the one GPU realm for both training and inference, at least in IceCube. Maybe we're going to a whole machine, but not, multi-node, large-scale clusters of GPUs is not something that we have been requested so far. We do have a lot of in-house GPU resources in IceCube, but they're focused on FP32 compute because that's what we use them for. Previously, we do have a handful of sort of more quote unquote modern cards, but most of our stuff is fairly old in terms of speed. There's also this whole thing for us, at least, that these high-end AI GPUs, your A100s, H100s, B100s, et cetera, are really not cost effective for us just because the FP32 compute has been decreased over time to add more and more AI features. And of course, this demand for multi-node, multi-GPU training has not really crystallized yet. That's why when we do have these demands or these requests, we usually offload them to things like Access or other institutional resources that we have access to, that provide these higher end things for larger groups. So sort of we're being more cost effective there. The GPU utilization is really a big issue. There's significant software and workflow effort that has to go into utilizing training resources fully. We've been testing this out, and I mean, just keeping the GPU at 20% is already a struggle for some of our folks. So really, that is really an issue. But similarly for AI inference, you're buying machines that are $500,000 each, and then you're using them at like 10% levels. That doesn't seem like a good investment. And this also comes in at inference. As I said, this is all high throughput oriented for inference, meaning that you really want to go through a lot of data very quickly, and that there are things like this idea of AI inference as a service. This is something that has been known as Sonic within the CMS community or the LSC community. It's inference as a service is also quoted in the Genesis mission we've just heard about. And then sort of part of A3D3, which is also an NSF investment into an HDR institute, we've been sort of exploring how we can use these sort of like as a service ideas to accelerate our GPU utilization. The other big thing is AI inference at the South Pole, because we are at this sort of like remote location. We have a power constraint. The environment is very challenging for electronics. It's very dry. It's the average humidity is below 5%. So it is very difficult to kind of, and we really need to explore how to really get that and how to integrate this whole thing in terms of software and hardware at the South Pole for these systems. From a software lens, sort of software CI lens, this is the great tools at this point for code developments. We want to write me something and it spits you something out. I want to do some training. It will give you, multiple files, multiple documentation, multiple things. I mean, you still have to iterate through it, but I mean, the acceleration just from a time saving of not having to type it is immense. There are a lot of questions out there, how user-friendly is this? How does everybody have access to this? I mean, hosting some of these newer models is from a hardware, but also from a software side is very complicated. And it's difficult for us to kind of, put another thing in our tool bag while running the systems that we already are, and things like that. So we are having some ideas there. And there's also just, how do we actually use it? Can we just feed in logs and it will tell us what's wrong? How do we create AI agents and things like that? These are all things that people have to learn now, or new tools that people want to learn. But ultimately, we still have sort of a day-to-day operation, and that is really restricting us. And ultimately, the funding there, we need to keep the detector running, and that's our priority. So that sort of the learning pieces are falling behind. And that's it from my side right now.
Okay. Thanks, Benedikt. We have Leanne Guy from Rubin next. Would you please share your slides, please?
Okay, so my name is Leanne Guy. I'm going to talk to you about how we've been adopting AI at the Vera C. Rubin Observatory. I'll talk to you first a little bit about Rubin Observatory itself. Okay, so for those of you who don't know, Rubin Observatory is a large aperture wide field ground-based optical and near infrared observatory, which is based in Chile. It's on Cerro Pachon, very close to where the dark energy survey is, and at about 3,000 meters. This shows you a picture of it just here to the left. Its construction is, for all intents and purposes, complete. We've got a few small things that are still being finished off, but we've been in operations since October 2025. And the phase we're in right now is called early operations, where we're optimizing the system performance before we start the main survey. Rubin is comprised of three sort of high-level instruments. There's the telescope itself, which is an 8.4 meter main mirror wide aperture telescope. It's very compact, and a key feature of this, in addition to it being very wide, having a very large light collecting area, is that it has a very fast slew and settle rate of 4 seconds to an adjacent field. Mounted on the telescope is a camera with 6 filters. This is a 3.2 gigapixel camera, the biggest camera ever built for astronomy. It has a field of view of 9.6 square degrees, and if you want to try to picture that, think about looking up at the sky and seeing a full moon, and then picture 7 full moons across and 7 full moons high, and that gives you your 9.6 square degree field of view. It has a very fast readout of 2 seconds. This is needed in order to keep up with the fast slew rate. So if you're constantly taking images, you've got to read them out very fast as well. And all this is complemented by an automated data processing system. Each image is about 6.4 gigabytes. That's compressed per exposure. We collect roughly 20 terabytes per night, and over 10 years, this will result in a data set of 6 million images and a 15 petabyte catalog. And access to the data products produced by Rubin to the community is via a cloud-based science platform. The prime mission of Rubin Observatory is the legacy survey of space and time. This hasn't started yet, as we're still in our early optimization phase, but this will be a 10-year survey of the sky. It's called the Wide, Fast, Deep. It is a wide survey, it goes deep, and it's very fast, enabled by the very fast observatory. You can see on the right here, this shows you the area of sky that will be covered by Rubin Observatory. The green area is what we call the Wide, Fast, Deep. This is 18,000 square degrees, and this green area will be imaged fully every 3 nights for 10 years. After 10 years, there will be roughly 800 visits per pointing. And these visits will be distributed across the 7 bands. It's 800 across all bands. It goes very deep to a depth of 27.5 magnitude in the R band. There are also other areas you can see here with fewer visits over the 10 years. These are the dusty plane area and the very dense galactic plane, the South Celestial Pole, and also the North Ecliptic Spur, which is important for solar system science. The yellow areas go much deeper, but they're much narrower fields. We call these deep drilling fields. We have a much higher cadence of taking images in these fields, and they go much deeper than the Wide, Fast, Deep, but they are only small areas. All of this results in a vast astronomical data set of 60 gigabytes of raw images, 15 petabyte final catalog, 500 petabytes of image data products. And we will put this out to a community in roughly 10 releases over the 10 years. Roughly, we're looking at 1 per year, but we haven't done one yet, so we'll see how that goes. In addition to that, we release 10 million transient alerts per night. So we look at the sky, we take an image, and then we look to see if that image shows anything that's changed compared to a template image of that same region of the sky. And these are alerts, and we put these out, and these are meant to enable follow-up observations for rapidly changing or moving objects. We expect at this time to start the LSST survey around February, March of this year. And this vast astronomical data set was driven by a variety of different science motivators. It's not the typical astronomy where you have a science question and you design an experiment. These 4 vastly different science cases of cosmology, dark energy, dark matter, mapping the Milky Way, looking at the transient, fast-changing optical sky, and taking an inventory of our backyard, the solar system. These were all drivers in designing the system. And what this means is that the LSST dataset will enable this entire range of science. So there's very little astronomy that won't be enabled by the LSST dataset over the coming years. This is a high-level schematic. I won't go through all of it, but it's more of a reference here that shows you, how this data is processed. The data comes in as sequential 30-second images, approximately 20 terabytes per night. This goes to the LSST science pipelines, which process the data. We release prompt data products, and we release release data products. The prompt data products come out on 3 timescales. On a 60-second timescale, we release the alert stream that I just mentioned. 24 hours later, we have detailed catalogs corresponding to those events that were in the alert stream that give a lot more characteristics and properties. And then 80 hours later, we release the images. And the data releases come out roughly once every year. And these are all shared through community brokers for the alerts and through Rubin data access centers distributed throughout the world. Many of these run the Rubin Science platform, which is the user interface that sits at these data centers where the hardware is to process the data. In terms of talking about what we're using, what sort of AI adoption we have at the moment, I'm going to talk really about some of the AI projects we have around our key performance indicators. Right now, we're attempting to optimize our image quality and optimize our effective survey speed so that we can start the LSST and keep it running with the fidelity needed for 10 years. The image quality and the effective survey speed are 2 very high-level metrics that are very important for Rubin. The image quality characterizes the spatial resolution and gives us a measure of the information content in the images. And it is impacted by things like static objects, the environment, the wind, the turbulence, the tracking ability of the telescope, charge diffusion in sensors, dome seeing, etc. And it impacts almost every aspect of the science that you do. So image depth, star galaxy classification, astrometry, blending. This all impacts all the different types of science harvest you would want to do. So getting image quality as good as we can is extremely important. And then there's the effective survey speed, which is the product of the ability to capture photons, which is the effective area by the field of view, combined with the observing efficiency, combined with the system availability. So sometimes the system will go down for maintenance and so forth. And so we define this metric here, which essentially gives us an indication of how fast we are progressing through that survey. Are we on schedule? And so we've had a number of AI projects around these themes that have been started up recently. This first one I'll mention is wavefront estimation with the Rubin active optics system. So Rubin uses an active optics system to correct the alignment and mirror surface perturbations that are introduced by gravity and temperature gradients in our optical system. This is necessary to give very, very high precision images. The wavefront sensor, it records these intra and extra focal images. We call them donuts that you can see here in this picture. And the team here, led by John Franklin Crenshaw and Andy Connolly at the University of Washington, have developed a deep learning model for wavefront estimation in the pipeline, which is more robust and faster than the baseline algorithm that's been used for many years. So basically, you take these donuts, these intra or extra focal images of the wavefront, you pass it through a convolutional neural net. This generates a set of features about the donut image itself. And then it concatenates those with a whole lot of other information, like is it intra or extra focal? What is its position? What is its wavelength? And it passes this information through a dense neural network, which estimates what we call Zernike coefficients. And these Zernike coefficients give an estimation of how much an image is different from an ideal in-focus image. And then that allows us to put corrections through the active optics system to bring the image in focus. And here we just show you some of the early results here. This deep learning approach has achieved an atmospheric error flow, even in very challenging atmospheric conditions, and a speed of up to 40 times that of the baseline model. And so this gray here shows you the theoretical error flow in atmospheric turbulence. The black line shows you where we need to be. We need the peak of our distribution of the error to be below this in order to achieve the image quality necessary. This shows you the AI approach, which is achieving that goal as compared with what we're now calling the previous state of the art, which did not use any sort of AI or deep learning approach. So this is really positive, and this is helping us to get towards very high precision images, which will enable a lot of groundbreaking new science. So complementing that, we also have louvers on the machine. There's on the system, if you look up on the dome, there's a lot of louvers which will let the air flow through. Air turbulence and air temperature is extremely important to image quality. And Marina Pavlovich is developing a machine learning model to try to reduce dome turbulence to optimize our delivered image quality. She's using this to try to predict what the image quality would be from environmental conditions, and then use a machine learned model to predict what the optimal opening angle of the louvers are in order to get the best image quality out of the atmospheric conditions. And you can see here that she's been comparing two models, the light GBM model, which predicts a uniform louver angle of 50 degrees. And here we also have the FF neural net model, which predicts different opening angles for different louver models. And so this is an ongoing project that we're looking at, but if we can develop a model that predicts the correct louver opening angles, we can change those opening angles as we observe and minimize the impact of atmospheric turbulence on the images. Moving on to the survey speed and how we would execute the survey. Rubin's survey is fully automated. It's automated by what we call a feature-based scheduler. We have designed a baseline schedule, which has been designed by the community, but this is executed automatically, and it takes into account evolving changes like environmental conditions, weather, system state, and designing multiple scientific priorities. So during the night, in response to the conditions, it uses a Markov decision process to rank candidate observations and decide what the best approach is. Once we get the data, that's about executing the survey. Once we collect data, we have this alert production system that produces something like 10 million transient events per night. And in amongst that, there are a lot of spurious events. And so this shows you the image differencing pipeline, where you take a template image of the sky, you take a new image of the sky, you subtract them, and you see that here there is an event that has changed. And so that's what we send out in the alerts. But how do we know whether this is an event that is a real astrophysical event, or how do we know whether it's a spurious event caused by a variety of system conditions or environmental conditions? The team have been developing a fast CNN to try to help eliminate false positives. This reliability model was developed with the aim to meet our latency requirements. We have very tight latency requirements with our alert production. We have to get our alerts out within 120 seconds and eventually 60 seconds. So this was developed to be able to run on CPUs, and it has shown enormous speed up in terms of processing 40,000 stamps per CCD. We have 189 CCDs in the focal plane, 40,000 little stamp cutouts of these detections. So this has been an enormous speed up, and it has given and it gives out a probability score, which shows you the reliability of whether an event is astrophysical or if it is not. You can find this, if you're interested in this, you can find this code in GitHub. It's open and freely available. So we've also been looking at how do we support our community by using AI. Rubin is big, not just in terms of its data or its variety of data or the size or the volume of data. It's also the community. We have something like 10,000 users worldwide, and a traditional help desk where people send in questions and wait for answers is not going to scale. So we've been looking at developing a generative AI chatbot for community support. We have a prototype of this built at the moment that is running on our cloud-based Rubin Science platform. It uses retrieval augmented generation. We have ingested a lot of data from Rubin that is very domain specific, and we've built a RAG system that then augments an existing LLM with domain specific knowledge and gives an answer back that, in principle, should be a lot more relevant. This is still in the prototyping stage. We make use of OpenAI for embeddings, Weaviate as a vector database, and we've currently worked with OpenAI as the generative LLM, and we have a front end based on Streamlit. So we ingest all of our information from Rubin through OpenAI into Weaviate, and then use that as part of this RAG system. So just to sum up now, at the moment, I'd say that AI adoption at Rubin is largely about scale. It's helping us to manage our volume, our velocity, our complexity, and helping us to make data-intensive workflows faster and more robust. This is a critical foundation for working effectively with big scientific data sets. However, as these methods improve and as we gain more experience, we will move beyond that into enabling discovery of rare phenomena. So adding insight, not just speeding things up or making things easier, but helping us to discover that rare needle in a haystack, anomalies revealing new science that wouldn't have been possible with previous techniques. And my last slide here, this is just a snapshot of some of the projects that use AI at Rubin Observatory moment. There are many, many others as well in various stages of development. So for example, we're looking at how we can do predictive maintenance with AI, photometric redshift estimation. There are many algorithms, and there are many people out in the community who are working on this, who are starting to use some early Rubin Observatory data to estimate photometric redshifts. Interpolation of PSFs for point spread functions between stars. We're looking at a project here. Scarlet 2 for deblending. This also makes use of deep learning models, etc., etc. Also, I'll just add that many staff are using AI coding tools integrated into our workflows. So GitHub Copilot, ChatGPT, etc., to accelerate development. Many have them integrated into their IDEs where they work every day. And this is sort of helping us to speed us along and do things faster and write code faster. And this is something that I think we'll continue to work with as we continue to adopt AI within Rubin. Thank you. Sorry for being a bit long.
No problem, Leanne. Nice talk. So we have Javier Duarte next from CMS.
Yes, I'll quickly kind of go over a brief overview of some of the places that AI has been adopted in the CMS experiment. And so talking about searching for new physics at the energy and intelligence frontiers. So of course the experiment I'll be talking about is located at is part of the Large Hadron Collider in Geneva, Switzerland, which is a proton-proton collider currently operating at 13.6 tera-electron volt center of mass energy. There are 4 interaction points located around the ring where there are different experiments, different detectors. So the CMS experiment, which I'll be talking about today, is on the left, is the star on the left. At each of these interaction points, there are about 40 million collisions per second. We can't basically store all these collisions. Basically the data storage cost would be too high. And fortunately, also the processes we're looking for are very rare, so we generally don't need to store every single collision. So as an example, one of the main things we study is the Higgs boson, which is produced about 1 out of every 10 billion collisions. So because of this high collision rate, we actually get a Higgs boson about every 4 minutes when the LHC is operating. And so in order to basically reduce the data set, we have a real-time trigger system or event filter system that's implemented on FPGAs on site. And this on FPGAs and as well as a CPU and GPU farm. So it's sort of 2 stages. And this reduces the data set down to about 1,000 collisions per second that is then stored for offline analysis. And the CMS experiment, sort of the head-on shot is shown here. It's about 3 stories tall. And it's composed of many different components and totaling 100 million channels to measure different kinds of particles. And on the right, you can sort of see the integrated luminosity. It's the way we measure sort of the size of the data set and how it increases during each data taking run. So we're currently in the midst of what's called Run 3, which has been extended for 1 more year. So we're going to take a little bit more data in 2026 before starting an extended 3-year shutdown in order to upgrade both our detectors as well as the LHC complex itself. And so the CMS experiments designed for a broad physics program ranging from measurements of the standard model and the Higgs boson, studies of heavy ion collisions, and searches for new particles and phenomena. And just to summarize, AI has been integrated into almost every aspect of our experiment. From simulation in computing to triggering, reconstruction, and analysis. I'll just basically try to highlight 3 examples of this, but you can imagine there's many other examples as well. So first, what the kind of data looks like is you have, so in this image, you have the proton beams coming in on each, on the top and the bottom. This is actually showing a potential Higgs boson pair production event. After basically the collision, we reconstruct tracks, cluster energy in the electromagnetic calorimeter as this electromagnetic interaction energy depicted here as these like green rectangles. Then we also reconstruct energy clusters in the hadron calorimeter. So this is this nuclear interaction energy shown in blue. And then we take all this information and we kind of can reconstruct higher level objects like potential jet jets, which are basically particle showers that are collimated. And so that's what you see as these orange cones. And then what we can try to do is basically identify the origin of these jets. So they might be from kind of mundane quarks or gluons, which generally we want to reject, or they could be coming from a Higgs boson that then decays to two bottom quarks, which is generally what we want to preserve. And so AI is actually, as you can imagine, used quite heavily in this kind of pattern recognition task. And in particular, just to kind of like show the evolution of AI specifically for this task, because it's kind of a benchmark task in collider physics, is we've kind of gone to lower and lower level of information from the detector in order to improve our jet classification capabilities. So again, you have this like image of it. You have this picture of a jet. So initially, a lot of machine learning algorithms were trained in kind of simple, shallow neural networks or boosted decision trees based on high-level features that were kind of expertly engineered. Subsequently, people started looking at like taking sequences and maybe looking at like RNNs. Similarly, taking images of like basically the calorimeter image in 2D and feeding that into like a CNN. And then finally, nowadays, people are kind of taking all the particles that are reconstructed, as well as maybe other sets of objects like vertices that are associated to the jet, and throwing this, as either a graph structured data set or as a sequence structured data set, and throwing this into a graph neural network or a transformer. And so I like this illustration of kind of how much our jet tagging has improved. This is basically showing the B tagging, a B tagging algorithm. So an algorithm is trying to tag basically bottom quark jets, and showing how much better the rejection of sort of so-called light jets in yellow, or charm jets, which are a little bit harder to reject, in orange or in red. And so you can see basically the light jet rejection has improved by basically a factor of 200 since kind of the early days of the shallow machine learning. And similarly, the charm jet rejection has improved by about a factor of 10. And these kinds of algorithms have like direct impact on the physics program. So for instance, in an example of a search for a Higgs boson pair production, which is really important to measure the Higgs boson self-interaction. So that's one of the key reasons the LHC is being upgraded, is to basically be able to measure this interaction. You can see that it actually improved a lot the capability to try to look for Higgs boson pair production in this channel where the two Higgs bosons decay to bottom quarks. And so this is showing a search using the run2 data, and you can see basically a small hint of a signal in the red histogram in this mass distribution. And this ended up being one of the best, most sensitive searches for di-Higgs production in LHC run2, which wouldn't have been possible without these AI algorithms. Another use case is actually deploying real-time anomaly detection in the FPGAs. And so there's an algorithm currently deployed taking data based on a variational autoencoder. And again, this is trained basically in an unsupervised fashion on real data. And then it's basically trained to essentially flag anomalies, things that have a high loss value relative to the rest of the data set. What's interesting is it's selecting kind of unique events relative to existing triggers. And so this can be used to search for like exotic new phenomena that may not be preserved by the existing triggers. And there's also the potential to sort of release this data set as kind of like a catalog of events for other people in the community to look at. And then as like a last example, particle reconstruction itself, which is basically the task where we take the tracks and the energy clusters that we reconstruct, and we try to infer which set of particles was actually produced in the collision. This can be formulated as an AI task, and this is nice because it's naturally tunable through retraining, and it can be portable to new hardware like GPUs. And so the goal is to basically learn a set-to-set function where you go from this set of tracks and clusters to the set of particles. And that's kind of depicted in this image. And this has actually been done using CMS simulation. And what we find is that there's an improved physics performance as well as computational scaling with this AI-based algorithm. So that's shown in the left by basically the transverse momentum, the resolution of the transverse momentum for a jet is shown in the red histogram compared to that for the traditional um, particle reconstruction algorithm. And you can see basically the distribution is narrower, so we have a better resolution. And similarly on the right, you can see basically the machine learning based runtime on GPUs. I should emphasize this is comparing two different hardwares as well. GPU, the ML algorithm which can natively run on GPUs versus the traditional algorithm which is running on CPUs. And the reason to like show it like this, there's a lot of white space, is basically to show that the scaling is a lot less it's a lot less linear. It's a lot flatter basically. So we can go to larger events and basically maintain the same time performance. And then finally, this is mentioned by Benedikt already, but there is kind of a need for accelerated inference as a service. And so there's the services for optimized network inference on coprocessors, or SONIC project, as well as related supersonic project, to implement basically server infrastructure for inference as a service application in large experiments. And so this is designed for deployment at Kubernetes clusters equipped with GPUs, and the sort of diagram for that is shown on the right. And as an example, this can be implemented in like the CMS software for reconstruction. And on the left, it's showing basically what, that you can basically get increased throughput for using basically this GPU inference as a service over sort of using on-site or traditional CPUs. And that's all I have. So thank you.
Thank you, Javier. Excellent diversity of AI use cases from the infrastructure side, from the science side. It's really exciting. We'll have Krishna Kumar next from TAC and Neri.
Krishna Kumar, I'm an associate professor at UT Austin, and I'm involved with the NSF NERI DesignSafe cyber infrastructure, and we'll talk about some of the AI work that is happening from the infrastructure side when dealing with like massive heterogeneous data sets. So DesignSafe cyber infrastructure has been around for the last 10 years. It has four main components catering to the needs of the natural hazard research, science, engineering, and management community. We do host a huge amount of data sets, almost like 4 petabytes of data set, human curated experimental facilities, simulations, and also rapid reconnaissance facilities. The unique aspect of DesignSafe is not only do you have a data set, you actually have a simulation and data analytics platform that directly plugs into this data set, sitting on top of the TAC hardware infrastructure. Then there's also reconnaissance results, which are published directly after a massive natural hazard, allowing people to understand what happened and also do planning measures. So we have about 10,000 users and 50 million files, about 4.5 petabytes of data. So we have a huge amount of data, and I'm also going to talk about the diversity of those data sets and people running enormous number of simulations and compute. And our goal is to make sure that these data sets are used, reused, and potentially discover knowledge from these data sets. So when someone published, for example, like the 2025 LA wildfire data set, that gets immediately published, and we want to be able to mine and understand what is happening and allow people to bring more knowledge from these data sets. So although these data sets can be sometimes small to really large, some can have like this ArcStorm simulation has, I think, like 2 terabytes of data set that was uploaded. So we want to make this data set available and queryable relatively easily. So we'll start off with like a simple query. This is our classic lexical search. I wanted to search for wind hazard data sets which have been published, or data sets around 2021. When I do that, I'm able to hit an Elasticsearch endpoint and then be able to identify a wind mitigation strategy for low-rise building. I was looking for 2021, ended up probably a 2021 data set published much later, but there's more than one data set, and lexical search is kind of limiting. What we are more interested in is trying to find out what are our missing gaps and knowledges. And in order to do that, we need to go beyond just doing text search on the data fields, the fields that could be metadata, author information, descriptions that the authors generally provide, to offering something much more intuitive and novel. So our first activity started closer to when GPT-3 got released. In 2023, where we were attempting to create a understanding or knowledge of this data set using GPT-3, but let's say we'll start with just regular structured data set, because people upload images, people upload experimental data, numerical simulations, we have videos, drone flights, LiDAR scans. So we thought, okay, if we were to extract information, let's start somewhere where we know things are structured. So we started and said, okay, starting with just CSV and spreadsheets, let's extract and build a semantic search engine where we can query and understand what are the interconnections in these data sets. So we took what is called as the LEAP centrifuge data sets. This is like done across 10 different universities across the globe. And these were standardized experiments. They were doing the same measurements across multiple universities in multiple countries. And then they curated these huge data sets across 400 projects and about 2,000 files. So what I want to bring your attention is like these data sets are curated, and they are curated based on different data models. And you can see here model configuration, sensor and events, and each event has its own file name. But you start to notice that there are interesting file names here. And one particular here, E0601, that's a very crucial information about what type of soil this test was done on. That represents the initial void ratio of 0.601. And sigma V is the stress under which the test was done. Unfortunately, information like these, especially when curated by non-experts, means they are going to hide or bury useful information like this in the file names. So how do we extract these information? So one of the things we started to do was trying to map out what is the domain knowledge. So we started to read or use LLMs to read the papers which the authors have published. And also to create context, we were reading information and building a structured queryable knowledge graph on top of this so that we can build an ontology to map out what the authors are actually doing when they upload a data set. So first, mine through scientific corpus to create named entity recognitions, and then build a knowledge graph. So we know, for example, when they mean axial stress and normal stress, they're talking about the same thing. That allows us to map different entities together. We did run into like interesting data curation where people will start putting columnar data with row data together, and that caused data extraction issues, although we were only looking for like mean, median, and some statistical descriptions of what's in the data sets. Once we had these and we were able to extract the information from the structured data sets into a JSON format, we were able to convert it or even check it against validators like Pydantic and use that to build our initial knowledge graph. Our current knowledge graph spans across all the 1,800 projects that have been published, but not all of it goes into these level of details, as it requires us to understand different domain knowledges, for example, from earthquakes to wildfires to flooding, and understand what those different terms mean. So our current search architecture, where user asks a question, we basically do an intent analysis to understand whether they are looking for a data issue, or they are looking at our documentation, or they want to run a simulation type architecture. And we use a 3-level search. One is a Lucine's lexical search. We also have the knowledge graph built on Neo4j to be able to query a graph database so that we can pull all the related information. Then we have a score function, which then gets fed into a GPT for right now. And we are also trying to build our own local inference engines so that we don't have to push it out to the final engine. So when you ask a query like this, the first step is intent analysis. We hit our Elastic API endpoints to understand like what are they looking for. So wind, hazard, and dataset goes as the search terms for our Elasticsearch, and we are also extracting out dates and author names so we can hit our knowledge graph a little better. And you can see here for the same question, like we're able to identify and extract all the related data sets, information which were published in 2021, compared to the information that we were getting purely using just text search. We've been extending this to not just the metadata fields that is published across our 1,800 projects. We also host quite a few structured SQL queries. And when users use Jupyter Notebooks and ask about it, most of our domain experts have to learn SQL, or we were trying to say, okay, what if you could query in natural language? But unfortunately, you have to load up the context, and sometimes these queries mean that the context window is too huge, with like 5,000 columns and so on. So we started building again, like a graph of all the columns, all the tables, and we basically solve a shortest path algorithm to figure out what type of SQL query joins I should do. So when a user types in, like, give me a table related to CPT data, it basically creates that graph query, finds the shortest path, and then executes that join statement so that now they can extract the data set directly in the Jupyter interface, where without having to leave that DesignSafe user interface or a chat window. Wanted to show a few other applications that we're currently working on is help users build automated workflows. These were our preliminary trials where they can take all the existing data set and say, I want to run this and check the analysis. And we are building parameterized Jupyter notebooks that allows us to string together and also verify if a particular workflow can be run using MPC and APIs that we're building. The final one, this is more exploratory than currently deployed, is we want people to understand natural hazards and explore scenarios or what-if conditions really quickly. So to ask for simulate 3D water interaction with Pagoda, an LLM agent will be able to generatively develop a full-blown 3D model and meshing system, and that composes with our own hybrid solvers like graph neural networks and NPM. So this whole pipeline from saying simulate a 3D water interaction to Pagoda happens in about 5 minutes, and you're able to go from just text to looking at what is the interactions of these. You can also use videos directly collected from construction sites or natural hazard sites, and extract those features. So identify which one's metal, which one's glass, apply the correct material properties, and hit those videos or objects with a natural hazard scenario, in this case, like a storm surge or a tsunami affecting an infrastructure system. So a lot of our LLMs are already deployed on DesignSafe and is readily available for users. And we are currently working on improving our workflows with LLMs and using generative AI to make it faster to go from collected data of natural hazards to simulations. Thank you very much.
Great. Thank you, Krishna. It was a nice set of use cases. both from a data management and data querying perspective to running the simulations as well, right? So I think that's great. So we have heard 4 talks and using an adoption of AI within the facilities from different perspectives, uh, doing the science, querying the data, getting better processes. So I think at this point we'd like to start with a short Zoom poll. Just a one question Zoom poll. Nikki is going to share to kickstart the Q&A session. So I'll give everyone a minute or two to respond to the question, and then we can start with the Q&A.
Is it okay to ask a quick question in the meantime?
Yeah, sure.
I was wondering, Krishna, a wonderful presentation for the building the knowledge graph and for embedding pieces. I was wondering if you had any issues in confirming whether all the papers that you were adding to your embedding space were under an open license.
So we were using either archive versions, so we could check the license, and we were also only using papers which are already published under open source for those data sets. So that was a limited attempt, but even to go to a subdomain of liquefaction, which is under earthquakes, under geotech, we had to get like few hundred papers to map the data. But that allowed us to see the scale of problem we are dealing with and what we need to do, because the big issue, what we were running into was people would say normal stress and axial stress to mean the same thing, and I have like 5 other definitions that are the same, and we were missing those if I didn't do those. Yeah.
Got it. And one last follow-up on that same thing, the same example that you gave, since you're talking about axial stress and like the other one, are you creating artifacts like ontologies that are basically being stored as local files? That way you don't have to run that check again.
Yes.
And it's kind of is building over a period of time.
So we've been building a ontology or taxonomy in that area. And what was interesting was when we started building it for just the experimental data model, the taxonomy we ended up having and the taxonomy our model curator had almost matched. And she was quite excited and surprised, but also worried that the taxonomies were starting to come together.
Awesome. No, that's really great. With all the work being done on metadata right now, the taxonomy match is like a big thing. So thank you for that.
Thank you.
All right. So I think we can end the poll.
Yeah. Give me 1 second. Sorry.
Yeah, so Nikki's going to share the results. We need to drop roll, I think, for this meeting.
It's coming. It's coming. I got signed out when I updated my.
Okay, maybe we can take a question, Jameson.
Yes.
Yeah, thank you. I mean, are you taking questions for the panel right now?
Yes.
Okay, good. So AI has become this extremely broad term that I think is kind of unhelpful. It's become unhelpfully broad. And there's a particular distinction which I make personally between essentially in-house trained, networks, deep networks, that kind of thing, versus commercially trained large language models. And I think a lot of people kind of think of them in the same pool, but they seem very different to me. And the approach to the use of them from a cyber infrastructure perspective seems like they should be handled quite differently. So I work for the LIGO project, and we have a lot of concerns, or at least some of us do, about the use of commercially trained large language models in the generation of code that we use to operate the instrument or do analysis, since the trend seems to be, sort of letting these black box commercially trained agents do things without much oversight. And we're quite concerned about that within the LIGO project. So I'm actually curious from the panel's perspective how they're approaching that distinction. I have not much concern about how projects use AIs that they're training themselves, but I'm particularly concerned about, or curious about, how projects are approaching the use of code generated by commercially trained large language models. So I don't know, like from a security perspective, from a operational safety perspective. So I don't know if any of the panelists would be willing to talk about that.
Benedikt, I see your hand up. I also see
I think
Leanne's.
Leanne was first.
Yeah. Yes, Leanne.
Hi, hello. Can you hear me?
Yes.
Am I?
Yes,
Yes.
Leanne.
Okay. Yeah, that's a great question. Thanks. I also agree with you that when we train models ourselves, we know how they were trained, so we understand the caveats, the risks. I think that we're in a good position to manage those. If you ask an LLM a question about Rubin Observatory or any of the research or science that we're doing, if you go to an LLM and ask it to generate you some code to use the Rubin data butler to access the data preview 1 data, it will generally give you a not very good answer. And that's a lot of what motivated us to try this RAG project, to try to build a chatbot that built on top of LLMs, but for our community, because ultimately we're finding that there were a lot of incorrect answers coming out of commercially trained LLMs.
Benedikt?
So I mean, so there's a couple. It's hard to unpack here. I mean, you could say the same thing about the new employee that you just hired. Do you trust their code to do the right thing? I mean, ultimately, in a place like IceCube, where a lot of the sort of science code, let me put it this way, is contributed by students, and we have very little control over the tools that they use or methods that they use. I mean, there's no way around it in some respects. We have to expect that, there will be LLM followed by coded stuff in there. And I mean, ultimately, it is who's going to shoot themselves in the foot first in some respects. We assume, I mean, as long as the tests pass, that the code is within reason. I mean, and I think that is, if you hire anybody, you kind, at least in the beginning, you have the same thing. I mean, from an operational point of view, I mean, you should always have, how should I put this, a good code testing environment and code review environment. So if it's something central like your data acquisition system or something like that, I mean, somebody's going to vibe code something into it. But ultimately, I mean, there should be a human, or at least 2 humans in the middle there before the code goes out into production. And I feel like, it is with any other code that you write or that somebody writes. You never know if there's a bug, if it's better. I mean, it's ultimately the big thing is the code might not phone home. It can't phone home necessarily, even if it's written by an LLM. unless you're not being careful. So that is really the thing that I look at. You should have the systems in place that you can say that this code is LLM produced, or this code does not, or rather answer the question of, does this code work as advertised, yes or no, and independent of if it's written by a human or an LLM in that sense.
Yeah.
Yeah, go
Oh,
ahead.
can I respond really quick?
Yeah, sure.
Yeah, so I guess I would dispute a little bit that an LLM can be just treated as a new employee. I really I'm not willing to take on faith that a corporate trained LLM has the same value system or loyalty or whatever, ethical framework, anything that a new employee has. But we don't have to get into that, sort of philosophical discussion.
This is a philosophical. I'm sorry, but at the end of the day, we're not handling the nuclear codes. We're not dealing with health, with somebody's life or something like that. I understand that some people see it as, you could destroy the experiment to some order, but at that point, that can happen with any employee, even somebody who's been there for 20 years.
Right, but I think that I guess this is part of it, which is that in previous time, before AI, I think I would have had more faith that new employees would, ask questions if they don't understand the systems they're interacting with. I don't have that faith anymore because I have seen people generate code through LLMs and try to deploy it with some sort of unnatural confidence. And so I guess this kind of gets at my question, which is that the requirements for review, for oversight seem much more stringent now from my perspective than they were previously. So how these projects, how your projects are attempting to mitigate that, what I see as an additional risk is what I'm curious about. I think that yes, in principle, we should all be doing review and we should all have full testing and stuff like that. I think we were able to, in some sense, get away with that in the past by assuming the best intentions of the employees, but I don't think that we can make that assumption anymore. So I think that the level of testing and review that we were able to get away with previously is insufficient. And so it actually comes off to me as a counterbalance between the supposed efficiency and productivity improvements that are coming with AI, that we actually need more review and oversight than we've had previously, which counterbalances the supposed productivity increase.
I think in the interest of time, we're almost out of time for this panel. We on Friday we have a good chunk of time to have a great conversation on this topic, and also we can take this offline. And I think it's an important topic, right? Because it's a balance between productivity and efficiency increase versus more efforts in verification and validation, right? So I think that's a topic that's interesting to discuss. But maybe in the interest of time, I will have one more question from the audience before we adjourn this panel. Any other questions? Okay, I don't see.
John has a comment in the chat.
Yes. Yes, it's on the same topic. I guess it's a very popular one. So, okay, I think In that case, we've run a little bit over for this panel. I really want to thank all the panelists, Benedikt, Leanne, Javier, and Krishna, for giving some excellent perspectives of AI adoption within your context. And I think the discussion, the follow-up discussions are also useful. We will, because there are many responses for the poll, I think we are going to collate the responses and send that over email to the participants. Thank you again for joining the panel, and I'll hand it over to Jarek, who is going to lead the next panel. Thank you. Thank you.
Thank you.